Hello everyone, welcome to QFT seminar. Today we have Monica Guica from IPhT Saclay. She will be talking about JTbar, deformed CFTs as non-local CFTs. Over to you, Monica.
Okay, so thank you very much for the invitation to give a talk. So I'll be discussing some work that I've been doing over the past couple years or so. The first paper in the series was written in collaboration with Ruben Monten, who is a postdoc at UCLA. And then I wrote some papers by myself. And basically the subject is exploring some infinite symmetries of certain non-local theories of which I think are of interest. So I should say before I start, maybe the subject is slightly confusing, so please ask questions. It's way better. Okay, so let me start by just sort of try to explain what the title means. Oh, yeah, very good. So for that, I'll start with introducing sort of the framework for these non-local theories, which, as you see, is quite different from the standard framework of local UV complete QFT. So in the standard framework, if I ask you to come up with some, local QFT that's UV complete, what most likely you'll be doing is to, start with some conformal field theory in the ultraviolet, and then deform this with a relevant operator. This triggers an RG flow, and somewhere down the RG flow is your local QFT of interest. And it should be complete by construction. The theories that I'll be discussing are constructed in a very different manner, which is basically opposite. So instead, what one does, one starts with the conformal field theory in the infrared, and then adds to it an irrelevant deformation. So now, normally or generically, relevant deformations are kind of ill-defined or not very well defined for at least a couple of reasons. One reason is that, if you try to add this deformation in sort of perturbation theory, at each order in the expansion, you're going to get some new types of divergences, which you need to absorb to some counter terms, and the number of those sort of proliferates. So one soon loses control over the relevant deformation. The second problem is that even if you manage to specify the deformation in some way, most theories that you get as such do not make sense at high energy. So there are theories with the cutoffs beyond some energy. You need to do something with them, otherwise they don't make sense. So these theories that I will be discussing in this talk are...
Sorry, Monica, just a little more detail on that. So what would the theory violate unitarity, or would you hit a singularity, or both?
So sometimes, I guess very often you need to be adding in some new degrees of freedom in order to solve some problem. Yeah, for example, with unitarity, for example. Yeah.
I see. So if I just sort of follow a renormalization group flow up by specifying some path very precisely, at some point you say you would either hit a singularity or get S matrices that violate unitarity.
I'm saying generically that's what you expect, right? Okay. Generically, and I'll make this point more precise later, but this is not an RG flow up the flow.
Okay.
But yeah. So the theories I will be discussing are like very, very special in that, first of all, there exists a way of specifying this, irrelevant flow. So that, there's an unambiguous way to specify what the deformation is, even at finite parameter. And second of all, if one picks some theory along this line of theories that I've drawn here, and goes to, arbitrarily high energy, there's nothing particularly wrong with the theory. So the observables seem to be well defined, like S matrix and stuff like that. However, these observables are not those of a local CFT. So the theory that you get like this appears to be UV complete. However, its UV behavior is not governed by a local CFT fixed point. It's intrinsically non-local in the UV. And the scale of non-locality is sort of fixed by the coefficient of the irrelevant deformation. it's a dimensionful coefficient. So one point about this RG flow business. So these two drawings, which are basically flows in the space of theories, may look similar, but they're actually very different. And maybe it wasn't a good idea to compare them. Here one has an RG flow. So one integrates out degrees of freedom to get from the theory over here to the theory over here. Whereas here one just adds the deformation to the action, but doesn't put in or out any degrees of freedom. So this is sort of an integrable flow, if you wish. And there are as many degrees of freedom in the theory over here as in the theory over here. And sort of that's sort of important in specifying. Okay, so this is basically what I'm going to talk about. Why are such theories interesting? For one, so there are these guys known as TTbar deformed CFTs, which seem to have something to do with QCD flux tubes. And that's, Dubovsky and collaborators did a lot of work on that. So this, non-local UV behavior does seem to be relevant for some nice physical systems. However, my main interest in this type of non-local UV complete QFTs defined this way stems from holography. And just to give you a rough holographic picture for what the dual is, I mean, we could start from here, which is something that you know very well. So over here, which are the standard RG flows, we can just translate this in holography by saying, oh, our UV CFT translates into some asymptotic ADS space-time. And then the relevant deformation is some way of continuing it in the interior. And then there's some rough equivalence or some rough map between the radial distance in the bulk and the RG scale on the boundary. Over here, if we play that game, what we get is that this IRCFT maps to some ADS space-time sort of in the infrared at the bottom of some throat. And then the irrelevant deformation, if it is single trace, then it maps to some non-normalizable deformation of this ADS. So that takes us out of ADS. However, this thing that I was saying that the theories that one gets along the flow are UV complete, and one doesn't need to add any new degrees of freedom to make sense of them, suggests that in the bulk picture, one doesn't go all the way out into asymptotically flat over here, but there exists some additional decoupling limit, such that the geometry in this decoupling limit is some non-ADS space-time, which would be dual to this, non-local UV complete theory that I drew over here. And okay, so my interest in this theory stems from the fact that maybe this sort of irrelevant flows could help us understand something about non-ADS holography. This is one way. Maybe it's not a simple way, but this is one way of trying to attack them, starting from ADS CFT as a continuous irrelevant deformation of ADS CFT. And as some people in the audience surely know, there do exist examples of such dualities of string theory. So non-commutative n equal to 4 super young means is an example. So you can write the non-commutative deformation as an infinite series of hugely finely tuned irrelevant deformations of n equal to 4. That's this picture. And it's dual to some space-time that's ADS5 in the IR and something non-ADS in the UV. But can people still hear me, by the way?
Yeah.
Yes.
Yeah, there's some noise. Okay.
That was me, Monica. Sorry.
That was you. I knew it was you. Nice to see you. Good. However, it should be pretty clear from what I've been saying so far is that trying to define an irrelevant deformation, a strong coupling, saying, oh, it's a infinitely finely tuned deformation that is chosen such that, my theory stays UV complete. That's a very difficult way of trying to define a theory. So it's basically hopeless. Okay, but anyway, so this was the motivation. This is what we wanted to study. But there's some hope that maybe the problem is a bit simpler if we work in 2 boundary and 3 space-time dimensions. So it turns out, so the motivation basically comes from, you know, the holographic analysis of certain string theory backgrounds, which for those interested come from the near horizons of some extremal non-supersymmetric black holes in string theory. And when you analyze these backgrounds, so these backgrounds admit these two decoupling limits, the usual ADS3 decoupling limit, but then there's some additional decoupling limit in the UV, which gives you some non-ADS spacetime. So this spacetime is precisely dual to such sort of flow, and that's okay, generated by some irrelevant operator. But interestingly, so now you can just use some basic holographic tools to try to infer the properties of the theory over here from just the bulk. You don't really know the dictionary, but you can say a few things such as, you know, what are the asymptotic symmetries, what are the scattering. So this should tell you something about it. And curiously enough, the asymptotic symmetry group analysis gives two copies of the Virasoro algebra. And this is very surprising because I just told you that the theory over here is a non-local theory. So, you know, what does it mean that the non-local theory has two copies of the Virasoro algebra? Moreover, if you study scattering of these backgrounds, you get, so in momentum space, you get something that looks very much like a two-dimensional CFT two-point function, but where the dimensions of the corresponding operators, instead of being constants, there are some specific functions of the momentum. So this sort of rough holographic analysis suggests that, at least in these particular cases, the theories that one gets over here are some sort of quote-unquote non-local CFT. Like they're non-local theories, but they have some CFT-like features. And this is what we're interested in understanding. I mean, I can be a bit more precise. The really basic question that comes to mind when one sees this is, do non-local CFTs, whereby non-local CFT, I mean just a UV complete, in this case, two-dimensional non-local QFT with Virasoro times Virasoro symmetry, do such theories exist? That's sort of the basic question. So the answer can be yes or no. If it's no, too bad. If it's yes, then it's really interesting because you know, you have like about a zillion questions that you can try to answer once we establish that they exist. Possibly the first one is, how is this Virasoro symmetry reconciled with the non-locality of the theory? Of course, we think of Virasoro as being generated by local conformal transformations. So, you know, how can you have this in a non-local theory? What are the consequences of this non-local Virasoro on the observables, such as correlation functions? And then you can ask more highbrow questions like, in CFTs, of course, you have the power of CFTs stems from the fact that they have an axiomatic definition in terms of, you know, some primary operators and their properties. Can you come up with such an axiomatic definition here? And, you know, are there constraints? Can you classify all the theories that you can construct and so on? And finally, can you understand something about non-ADS holography after you've done all this? But basically, this talk is going to be a field theory talk. So holography was just a minute. And basically, the claims are that these theories, which go under the name of TTbar and JTbar deformed CFTs, are actually examples of non-local CFTs. So as I tried to explain a couple of slides ago, the really difficult part is trying to define the irrelevant flow. That's really hard in general. But fortunately for these theories, this part of the work was done for us by Smirnov and Zamolodchikov. So they came up with a well-defined irrelevance deformation up to finite parameter. So basically what we're going to do is just study the symmetries of these theories. And we can show that there's an infinite number of them. So in the case of TTbar, they fall into two commuting copies of the Virasoro algebra. And in the case of JTbar, it's two commuting copies of Virasoro Kac Moody. And classically, the symmetries are basically implemented by field-dependent generalizations of the standard conformal transformations of 2D CFTs. We call this transformation pseudo-conformal. Okay, so these are the symmetries. And finally, at least in JTbar, JTbar. It turns out that JTbar is much simpler to study than TTbar. We can come up with some sort of notion of a primary operator, and then we can compute correlation functions of these primary operators. They turn out to be entirely fixed by the correlation functions of the undeformed CFT. And what they look like, at least at the level of low point function, like 2 and 3 point function, they look exactly like, in momentum space, they look exactly like the CFT 2 and 3 point functions, but with the dimensions replaced by some particular function of the momentum, some momentum dependent conformal dimension. So, okay, we're happy. At least, I mean, this is not exactly like in you know, the black hole picture I was talking about, but at least we see that there might exist a mechanism for certain theories to produce momentum dependent conformal functions. Okay, so these are the claims. So is it clear what? Are there any questions about you know, what's the motivation and what I'm planning to do?
Just to understand, Monica, where does the negative sign TTbar fit in this? The thing that's usually called the holographic sign.
I mean, you can do it. So I'm not very interested in it. I mean, so how to say, to the extent that the theory exists and can be put on a cylinder, I don't really care about the sign. But you may worry that negative mu TTbar and JTbar are not terribly consistent once you put them on a cylinder because of the imaginary energies.
Right.
So
okay,
positive mu TTbar, I think that's probably the best defined theory.
Got it. Thank you.
So, Monica, suppose we took 24 free scalars and TTbar deformed that. At least I hear that becomes just the Nambu-Goto action with 24 free scalars, which we can rewrite then as 2D gravity coupled to 26 free scalars. So firstly, is that correct? And second, is one lesson from this that you end up getting two-dimensional gravity as the UV theory in some of these theories?
I don't know. I think it's a question whose answer is not well answered. So there are people who say, precisely because of the setup you mentioned, that TTbar is like a theory of 2D gravity. To me, it's not clear because to me, TTbar is really Nambu-Goto after you've gone to static gauge. So I think that's the presentation of the theory, and I mean you don't have a graviton in this theory. So, you know, it's hard to say whether it's a theory of gravity or not, because in 2 dimensions you don't have a graviton. And you know, you can raise state to the gravity by introducing 2 more bosons, but it's not clear whether you can always play that trick, right?
Okay, but maybe I can re-ask. So that in this case we could word it as local theory subject to some constraints. So is the non-locality that you're talking about basically the constraints?
Yeah, I think it's it's going to the static gauge that basically makes the theory non-local. It's non-local in kind of a trivial way. It's non-local in a way that's entirely determined by the seed theory, which is 24 free bosons.
Okay. Yeah.
Yeah. So I should say the way that I think about these deformations, I don't know if it's the correct way, but the way that I think about them, it's some sort of deformation that sort of changes the kinematic structure of the theory. For example, it makes it non-local, but it doesn't really affect the dynamics or the nature of the theory. It's just some deformation of the kinematic structure.
Okay, thank you.
But yeah, I unfortunately, I do not know the answer to your question, and I also don't think it's known. Maybe on Carlos, but my hope is that it's actually a non-local QFT rather than a gravity.
Okay, thank you.
Okay, but I have no proof. Okay, so the plan of the talk is the following. So I'll first briefly review the Smirnov homological deformations, but really briefly. So TTbar, JTbar, and also a really trivial one, which is 2U1 currents, which will be useful for you know, just pedagogical purposes. But this is not an irrelevant deformation. This is a marginal. Then I'm going to give you a general quantum mechanical proof of the existence of Virasoro symmetry in these theories. And then I'll talk a little bit about the relationship between these Virasoro generators and the generators of these pseudo-conformal transformations, the field-dependent coordinate transformations. Then I'll talk about primary operators in JTbar, and really briefly, time permitting, I think I just have one slide on this. Okay, so this is going to be like really short. So Smirnov's analogical deformations. So they are irrelevant deformations of two-dimensional QFTs, which are constructed as bilinears of two conserved currents. So I define this operator, which depends on the currents J, big A and big B. This is 1 and 2, if you wish. And this is defined as the coincidence limit of this particular anti-symmetric combination of the two current components, taking as they coincide. And what Smirnov's analogical showed that in this coincidence limit, what you get is some operator which comes with a constant coefficient. That's the Smirnov's analogical operator, and then everything else is a derivative, total derivative. So this defines the operator up to these total derivatives, and it turns out to have some really nice factorization. This is the operator. Now, to define the deformation, you basically add the operator to the action. And then you deform the theory in this very particular way. So in the undeformed theory, you just add this OJ, JB. And then once you've deformed, you recompute the conserved currents. You reform this antisymmetric combination, and then you deform by that operator. And so it's always deformed by the instantaneous, J, which JB. Smirnov's analogical operator. That's sort of important. And the nice thing, it turns out that this deformation is sort of well defined. And okay, so there are a couple of sort of very well discussed examples of these deformations, which are nice because they're universal. You can do them on pretty much any 2D QFT. One is the TTbar deformation, where the two currents correspond to different components of the stress tensor, and you anti-symmetrize to get something Lorentz invariant. So TTbar is a scalar dimension 4 operator in 2 dimensions. So it has some coupling, which is dimension length squared. And another thing that you can do this JTbar, where you take one current to be a U1 current, and the other current to be the components of the red moving stress tensor, this guy over here. The dimension of this operator is 1,2. And the nice thing about it is that when you act with it on CFTs, because it's sort of marginal on the left, it actually preserves the left conformal invariance of your original theory. So it breaks the right moving conformal invariance. It makes the theory non-local on the right, but on the left, you're left with a theory that's local and conformal. So this is the structure. Of course, Lorentz invariance is broken, but that's not so much of a problem. It turns out that the fact that you have locality on the left gives you a huge amount of control over the theory, which is the main reason that this deformation is much easier to study than this one. Okay. And finally, okay, so then there's this trivial example that I'll use for pedagogical purposes, J1 with J2 for 2 U1 currents. This is an exactly marginal deformation, and I mean, we'll just play with it. And in the case of these two guys, so this is exactly the flow picture that one gets. And the nice thing about these deformations is they are highly tractable. You can get an exact and universal formula for the finite side spectrum. For the S matrix, they preserve integrability if initially present. And basically from the formula for the S matrix, you get this idea that the theory, despite being non-local at the scale of set by the deformation, it's actually UV complete because you have a nice S matrix. Okay, so I'm not going to say a lot about these theories. Let me say one thing that's going to be quite important in one follow. Yeah.
So can I ask a question? You said that the deformation is by this OJJB operator at each point on the flow. You sort of recompute it and that is your new deformation, right? But if I try to express it in terms of the, let's say O of lambda in terms of the one before, as you know, how would that look like? Like if I try to if I try to express the O of lambda at a later lambda in terms of the one before.
You mean to compute like d by d lambda of lambda?
Yeah, right.
I'm not sure what that looks like. I mean, I guess it's computable because, I mean, at least classically, we have the full expression for this O of lambda at all lambdas. So we can just compute the derivative, but I'm not sure there's necessarily something nice.
Okay. And when you say it has nice factorization properties, you're thinking of correlation functions of these operators, or? Yeah,
so when you take the expectation value, so Zamolodchikov showed that when you put take the expectation value of this in some energy eigenstate,
they factorize
it factorizes between. Actually, you can see that from the following slide, which makes it. So this is something I got from Onkar's paper actually. So one of the nicest observables.
Monica, sorry, before you go on, please excuse me. I don't know if you can hear me or the hum is.
Yes, I do hear you. I'm sorry because I'm going at the speed of light. So yeah.
No. I'm clued out about these things. But let me ask you this: when you say it is non-local, what do you mean by that? Do signals propagate way outside the light cone? I mean, what does non-locality mean? Sometimes you can choose a bad gauge and a local theory can look non-local.
I mean, for me, so in the case of JTbar, there's something which is super clear.
Okay.
In JTbar, you still have this SL2 left local conformal invariance, and you can ask what are the dimensions of operators under this SL2 left. They become momentum dependent. They depend on the rewriting momentum. That's very clearly non-local. I think but then it is true that these theories also have depending on the background they might have superluminal propagation depending on where they propagate. I mean, yeah.
I see. Okay. So I mean, operationally they really are non-local. Huh? You create a disturbance and the effect really instantaneously gets somewhere else. Is that right? I mean, I'm just asking.
Yeah, there's another.
I don't want to slow you down. I was just trying to.
I'm gonna readdress it in 2 slides.
Okay.
No another example of non-locality in TTbar.
Okay. Yeah. Thank you.
Good.
Sorry, Monica. Probably very stupid question. When you say if J and J bar are conserved, and you deform by this. This is exactly marginal. Is that always true? I mean, of course, it's marginal, but is it always exactly marginal?
I don't think so. I mean, it depends what I'm really taking 2 U1 currents that have nothing to do with each other. I think you can cook up cases where I mean, people who study deformations of various 2 dimensions, I think they have a whole classification of, you know, current deformations, and sometimes they're not exactly marginal, but in my case they will be.
Okay, thank you.
Yeah, I don't. This is not supposed to be a universal statement. I'm just taking an example where this is exactly marginal, such that I can see.
Okay, thank you.
What I'm saying. Okay, good. So as I said, so one of the nicest observables to compute in these deformed theories, and that have been discussed a lot, are the finite size spectrum. So you basically put your deformed theory on a cylinder of radius r, and then you so basically what happens is that this is a sort of a smooth deformation that basically doesn't change the Hilbert space of the theory. It just changes what the Hamiltonian is and its, you know, eigenstates and eigenvalue. But basically you can just use first order quantum mechanical perturbation theory to write down some flow formula for the you know, energy eigenstates and so the energy eigenvalues and the eigenstates. So these are just basic quantum mechanics. And so these are just the you know, matrix elements of the deforming operator. So this d lambda of the Hamiltonian is nothing but the, you know, spatial integral of the Smirnov-Zamolodchikov operator I just showed, and these are the eigenstates. And it was shown in this paper that the Smirnov-Zamolodchikov deformations, this d lambda of H takes a very, very nice spatial form. So there's a term which is just a commutator with the Hamiltonian of something, and then the rest consists of an antisymmetric combination of just the spatial zero modes of the two currents. Okay, so basically what happens if you're trying to just compute the flow of the energies, this term doesn't contribute, and this term is responsible for this, universal spectrum that you get for each of these deformations, because this just depends on the zero modes. And for example, for TTbar deformed CFT, you get this exact formula for the deformed energies on the cylinder in terms of the undeformed energies in the moment. So that comes from this term. This term, as you can see from here, it actually contributes. It's one of the main contributions to the flow of the energy eigenstates. So I'm going to call this operator over here chi. So the eigenstates satisfy flow equation d lambda of n lambda is chi, which depends on which precise deformation I'm doing on n lambda. And this guy has a contribution from here. This g is just the Green's function on the cylinder, and these are the time components of the two currents. At least in the classical limit, this is what it is. And then depending on whether this operator is diagonal or not in the energy eigenbasis, you might get some extra contributions from it. Okay, but all of this was to say that we in principle know, at least in the classical limit, what this chi is, and that's going to be important. Okay, very good. So we can get the deformed energy spectrum. One can also get the deformed S matrix, which is related to this deformed spectrum via the thermodynamic Bethe-Ansatz equations. That's another nice result. And this works for TTbar, JTbar, random combinations thereof, and so on. This was shown very some additional properties. So I really don't have time to say anything terribly precise about these theories. One important one that was noticed early on is that the deformed and undeformed CFTs are related via field-dependent coordinate transformation, which is sort of universal. For each deformation, you get some type of relation between them. So in TTbar, the field-dependent coordinate transformation involves the integral of the stress tensor. This is basically the transformation that takes you from conformal gauge, which gives you the 24 free bosons, to the static gauge, which basically gives you the TTbar deformed free bosons. In JTbar, the coordinate transformation is much simpler. The left moving coordinate doesn't transform, and the right moving coordinate just gets shifted by lambda times the phi is basically the bosonization of the U1 current. Okay, and this picture basically was shown to basically be responsible to the fact that the S matrix just gets deformed by a phase, which is the guy that I've written over here in the case of TTbar. So in the TTbar, you basically get mu times roughly p squared. Yeah. So. As was already mentioned, there's this question about how non-local are these theories? Are they sort of non-local in a trivial way because one is using just the wrong variables to express them, or and so on. So it was shown in a very nice paper by Dubovsky and collaborators that this particular phase that one gets in the case of TTbar is responsible for a time delay in 2-2 scattering, which is proportional to the energy. So that sounds very much like sort of gravitational scattering. They also showed in the same paper that the same phase, when you do scattering of wave packets, it leads to a minimum length that you can discern. And I think that's a physical consequence of the non-locality. So even if the observables are very simple, they have a very, I think this is a non-trivial physical impact of this phase, and you cannot do away with it. You cannot say that this is the same as a local free boson. because of this minimum length that's induced by this particular phase associated to the TTbar deformation. So I don't know if that answers Standish's question.
Okay, no, thank you. So when you try to do scattering, you can't resolve more than a certain minimum length, you're saying?
Yeah, so they start with two wave packets which have the usual uncertainty relation between width and momentum spread.
Yeah.
And then they scatter them, and then they show that after they scatter, they have an uncertainty between basically the width of the two.
I see.
So is this solving the simplest theory of quantum gravity paper? Mm-hmm. So okay, so this sort of physical implications of the phase has suggested that maybe TTbar should be thought of as a theory of 2D quantum gravity. That's one possibility, but as I was telling to Shiraz, I mean, there's no graviton in 2 dimensions, so you don't really know what you're doing, and it's up to you whether you gauge or you don't gauge. So, so to me, it's not clear what the answer is. You also seem to get, so this is work by Cardi, which I forgot to write, that you have some nice flow equations for the correlation functions in the theory, which might suggest a structure that's more akin to that of a non-local QFT. So I don't know what the answer is. In JTbar, it seems that the answer is clearer, because in JTbar, you can just define correlation functions, like even very simple-mindedly. The theory is local on the left, so you can just, and non-local on the right, so you can work in terms of operators that are, depend on the left-moving coordinate and the right-moving momentum, and compute their correlation functions using this SL2 left, and this is what you find. So you find CFT1 correlators, because you're in momentum space on the right, with these momentum-dependent conformal dimensions, and again, that's a clear signature of the non-locality. Note that these dimensions look exactly like spectral flow with a momentum-dependent parameter. Okay, so these are some additional properties. I'm going uber slowly. So we'll see what happens. Okay, but okay, let me go to the next point and tell you about, prove to you that these theories actually have Virasoro symmetry. And the proof is like sort of abstract, and it goes back to this.
Sorry, Monica, just going back to the example of the TTbar deformation of 24 free scalars. One set of observables in those theories are integrated correlation functions, right? The kind we use in string theory. Right. Does this construction suggest other observables?
Yeah, I would think that, I mean, you see it in, if I get to the end of the talk, which is not clear, it seems that momentum space correlation functions. The way I think about this is like a bit like the non-commutative theories. You see, they're QFTs, but they're non-local, so you have to work in momentum space.
So you said that when you do that, you get many more observables, of which this is one example, of which these integrated.
Yeah, I think there's a one-to-one. In the case of JTbar, there's a one-to-one correspondence between your original local operators and these momentum space guys that I'm going to talk about.
Okay, thank you.
And the correlation functions are entirely determined. In TTbar, I hope the same is true, but TTbar is much harder to study. But yeah. Okay, so let me tell you about the symmetries. And as I said, this is an abstract argument whose departure point is this flow of the energy eigenstate. So I put my theory on the cylinder, and as I told you, the energy eigenstate and lambda flow with some operator chi, which importantly is assumed to be well-defined. A well-defined operator that's constructed from the Smirnov Zamorodchikov, as I showed. So here, what Onkar was asking at the beginning of the talk about negative mu TTbar, that will enter into how well-defined this operator is. So from this point of view of the flow equation, I'd say the positive mu TTbar is the best defined theory, but hopefully the others can be studied in some sort of arbitrary perturbative expansion in lambda. Okay, so what I want to do, I want to define some operators L tilde, L and tilde, which satisfy, which basically flow in the same way as the energy eigenstates with the same chi, and with the initial condition that at lambda equal to 0, they just equal the original CFT generators. So it's clear. This is just a definition, and it's clear. It's these guys are well defined because I'm just integrating this flow equation with this initial condition. And by construction, this ln tilde satisfy Virasoro or Virasoro Kac Moody squared algebra, depending on what I had initially, with the same central charge as that of the undeformed CFT. So this just follows from the Jacobi identities for chi. Another property of these operators is that if you look at L0 tilde, so L0 tilde on, H lambda, now it's the flow of a primary state in my original CFT. This guy has to flow in the same way as the primary. So the proportionality must be a constant, which is nothing but the eigenvalue of the undeformed CFT generator, L0. Okay. So L0 tilde on the flowed eigenstates, primary eigenstates is just the undeformed eigenvalue. Okay, good. So these are some formal properties. Well, I have some Virasoro generators, but I haven't shown to you that there are symmetries, because in order for them to be symmetries, I need to prove to you that the generators are conserved. So now let me show you that actually this satisfies the expected conservation equation, which is written over here. So what is so normally you might say that the symmetry corresponds to some operator that commute to the Hamiltonian, but that's not the most general requirement. Actually, in the case of space-time symmetries, for example, just standard Virasoro, you need this extra term which involves the explicit time derivative of the Schrödinger picture operator. In here, and this is the standard requirement for a conserved generator. Upon using Heisenberg's equations of motion, this is just d by dt of the Heisenberg picture operator. Okay, anyways, so this is what we want to show. And to show this, we need to compute this commutator. And the point is that this commutator actually follows from the fact that it turns out that the Hamiltonian in this theory is just a function of L0 tilde and L0 tilde bar, and then we can just compute this. So how do I show that the Hamiltonian is just a function of L0 tilde and this bar? Well, so according to an argument by Le Floch and Nézet, this basically follows from the universal spectrum of, say, TTbar deformed CFT. So I told you that when I put the theory on a cylinder, I have some universal formula for the deformed energy, which is nothing but the eigenvalue of H. In terms of the undeformed energy, which I've written over here, and momentum. And as I just explained, these guys are nothing but the eigenvalues of L0 tilde and L0 tilde bar in the deformed theory. And since this works for all the eigenstates in any theory with any spectrum, I can just extract this to an operator formula that relates H to L0 tilde and L0 tilde. Okay, so this is the inverted formula. And once I have it, I can trivially compute this commutator, and I get something that's proportional to, Lm tilde with some coefficient that depends on the Hamiltonian and the momentum. And this coefficient, I'm written it over here. It's, it's some ugly squared formula, but it's completely well defined. Note, since this is an operator, it changes form if I put it on the left or on the right. Okay, so once I have this commutator, I can sort of trivially cook up some time dependence for my generator, such that they satisfy this equation, and this is the answer. So it turns out that these guys with this time dependence, e to the I alpha t, are conserved. And since they are conserved and they satisfy the Virasoro algebra, it means that TTbar deformed CFTs possess Virasoro times Virasoro symmetry. Note that this argument is really no different from the ones we use in CFT. In CFT also, H with LM, so H is L0, so it's proportional to MLM. So we still need to add the time dependence. The only difference here is that, this guy is an operator that rather than being a constant. And the fact that this is an operator just follows from the fact that instead of having H be proportional to L0, H is this sort of nonlinear function of L0. But that's all.
Sorry, Monica, just one question. In the flow of the Hamiltonian, there's also the zero mode part, right? Which there's this chi term and then there's the zero mode part. My impression was that for TTbar in a cylinder, that zero mode part is not diagonal in the.
Yeah, that's indeed true. That's indeed true,
okay.
But we did manage to solve it. So that's work in progress.
Okay.
But we did manage to, yeah. So indeed. So what is? No, what's happening? Yeah, so what Onkar is talking about is this piece. Yeah, as I was saying, this guy will always contribute to chi, but then if this guy has non-diagonal elements in the energy eigenbasis, we need to, it's going to contribute to the definition of chi.
Right.
That happens in both JTbar and TTbar, but we know how to do it in both cases at the classical level.
Okay, okay. I see. Okay, thank you.
Yeah, it's just that it's not published for TTbar. Okay, very good. So, very good. So this was basically an abstract proof that this theory has Virasoro times Virasoro symmetry. And, you know, the same thing works perfectly well for J1 with J2 and JTbar. With the only, you know, note that whenever we have a local symmetry, like for these guys and also for the left moving side of JTbar, then these alphas just become numbers. Okay, we can also do this for the Kac Moody, so that the same thing happens. And what I find sort of intriguing is that this argument really doesn't take much to do, or something that doesn't look like it's a lot. All we need for it is that we have a smooth deformation of this eigenstate. So we have some sort of integrable deformation that doesn't change the Hilbert space, but just you know, Hamiltonian and eigenvalues. And then the second part of it is that L0 tilde, the zero mode of the Virasoros, is a function of the Hamiltonian and a few concept charges. Whenever that's true, that of course is a sort of strong requirement. Then we can show that that we have Virasoro symmetry. So it would be interesting to see whether this sort of argument can be generalized beyond you know, TTbar and JTbar, which are very special and slightly boring theories. Okay, so was it clear? Any questions about the argument? Okay, so assuming that the argument was clear, now I wanted to talk a little bit about, so now I give you an abstract argument that the theory has Virasoro symmetry, but you might ask, okay, how is this Virasoro symmetry implemented at the level of, you know, conformal transformations or their generalizations? So this is what I'm going to talk about. And this is where this J1 wedge J2 warm up is sort of maybe useful to get a little bit of intuition. And so we're going to do this, and actually we're going to work at classical level just to be able to write down everything very nicely. So we work in Hamiltonian language. Hamilton depends on some scalar fields and their conjugate momenta. And for the J1 wedge J2 deformation, this is the flow equation for the Hamiltonian, where the two currents are modeled as shift currents. So they have this component. Okay, so the point is the following. Starting from any undeformed Hamiltonian with two U1 shift symmetries, we can just solve this equation for the deformed Hamiltonian. We get this exact expression, and we can just compute also the chiral currents in the deformed theory. Remember, this theory is supposed to have, you know, Virasoro times 2 copies of Kac Moody. And okay, since we know everything about the theory, so the Virasoros, or the width, because we're classical, they're just the Fourier modes of the left moving Hamiltonian, and the currents are just Fourier modes of the left current. And then we can just ask the simple question. So I just told you, I give you an abstract argument that this theory has Virasoro symmetries that satisfies this flow equation by definition, where chi is defined as such. I can ask, do my classical Virasoros over here satisfy the classical limit of the flow equation with respect to this operator that was appearing in the flow of the energy? And the answer is that no, they don't satisfy this flow equation. And then you can ask, okay, but who satisfies the flow equation? It turns out that these particular combinations of the L's and J's satisfy the flow equation with respect to chi. And what these combinations are, they're basically spectral flow where the spectral flow parameter is proportional to the U1 charge. There are two U1 charges, which I'm calling this curly pi, and then they depend on the U1 charge. So you get a sort of an operator-dependent spectral flow, and you have to perform it in order to get the generators that satisfy the flow equation. Okay, and then one can check that the eigenvalue of L0 tilde on the deformed eigenstates is actually the original CFT eigenvalue, because you get some.
And just to understand, so, is the reason for these extra terms the zero mode, the subtlety with the zero mode part by any chance, or what's the reason there are these extra terms in the L tilde and J tilde?
What's the reason? So in the case of J1 with J2, the chi operator just comes from the second term. So the first. I think it's just in the structure of the. I mean, you see, you need the offset because when you do the deformation, the spectrum of the theory gets modified. But the flow equation tells you that the spectrum of L0 tilde is not modified. So it's clear you need to do some sort of offset to do it. So as I said, so this is the spectrum of the deformed theory. This is the spectrum of L0. And then you see that L0 tilde is L0 minus this thing, and basically it cancels away these guys.
Cool. Okay, thank you. Sorry.
Yeah, so it's just built in the structure of the theory, and it has to work out in this way in order for the eigenvalues of L0 tilde to be identical to those of the undeformed CFT. Okay, good. So this was the lesson in this trivial example where both sets satisfy Virasoro. We see that the flow, the generators, the guys that satisfy the nice flow equation are not exactly the standard Virasoro generators. You need to do this operator dependence. Okay, so then what happens in JTbar? Well, in JTbar, classically, we can just do exactly the same steps. So we solve the flow equation for the Hamiltonian density, where we model this U1 current by some topological U1 current, so some phi. We get an exact solution for the deformed Hamiltonian, which looks like this. So the deformed Hamiltonian expressed in terms of pi and phi prime, basically over here, and the undeformed Hamiltonian of the CFT. And then from this exact formula, you see that the Poisson brackets in the deformed theory are universal and entirely determined from those of the original CFT. They're universal because H is just a function of H0 and J plus, which have universal Poisson. So you're going to get something ugly, but universal. And you can compute. So here I gave you some examples of things you can compute. You can compute the commutator of the total Hamiltonian with the left and right Hamiltonian currents, and you get specific expressions like this. So now we can ask, okay, can I construct conserved charges in this theory? And again, since I'm looking at space-time symmetries, the condition to have a conserved charge is that it's Poisson bracket with the Hamiltonian plus or minus the explicit time dependence is 0. And on the left moving side, it's trivial to construct. So these are just the left moving symmetries, functions of the left moving coordinate into the left Hamiltonian. You can trivially check it satisfies this using this commutator. And same for the currents. So they satisfy with Kac Moody algebra. That's all very nice. However, on the right moving side, so on the right moving side, okay, you can do some guess. It turns out the correct guess is that you have some charges that look like translations. So this is what this H right is doing over here, but with some field-dependent coordinate in front. And now if you want this charge to be conserved, there's going to be some, for any F bar, you're going to get some condition on the field-dependent coordinate, little v. And this is basically the condition. This comes from charge conservation for any F bar. And then you can rewrite this as such, which makes it clear that the solution is the field-dependent coordinate is the right moving coordinate, sigma minus t, minus lambda times phi. I remind you that phi was the bosonization of the U. Okay, so you can see if you pick little v to be like this, it's a sort of a universal field-dependent coordinate in JTbar. And it gives you an infinite set of conserved charges for any F bar. Okay, so that was our first proposal, and it sort of works in infinite space. But we really want to study the symmetries of JTbar on the cylinder. And it turns out that on the cylinder, these charges are problematic. They're problematic when you're on the cylinder and you're trying to actually sort of semi-classically quantize the theory. So promote Poisson brackets to commutators. And the problem is that the commutator of these charges with the global U1 charge is inconsistent with U1 charge quantization. The problem basically comes from the fact that the U1 charge doesn't commute with the zero mode of phi that appears in the field-dependent coordinate, and that's creating all the problems. So the solution is basically to try to define a new field-dependent coordinate where you basically kick out the zero mode of phi out of here. That can actually be done. So it's a bit non-trivial because you also want to keep charge conservation. Okay, you get some ugly expressions, but you can do it. And it turns out that the new set of charges, so the ones computed with V improved over here, they're perfectly consistent with charge quantization and also momentum quantization. So that's good. So now we can ask, okay, what's the algebra of these charges? So the improved charges are the one with the double line notation over here, and we find some disgusting nonlinear modification of Kac Moody. It's really ugly. However, if we do these particular nonlinear redefinitions of the charges, so we take these nonlinear combinations of the charges, which are basically spectral flow by lambda times the right moving Hamiltonian, we find these Q tildes, which turn out to satisfy just two commuting copies of Kac Moody, and moreover, they satisfy the flow equation with respect to the classical limit of the JTbar operator. So to make a long story short, so first you have to be careful about how you define the charges such that you can actually consistently quantize the theory. This is a bit non-trivial because of the zero mode business, but we know how to solve it, and we also know how to solve it in TTbar actually. And then the charges that satisfy, the Virasoro algebra, the ones that I got from my general flow argument, are actually these particular nonlinear combinations of the charges that I'm initially constructing. Okay, so this is just the summary. So we can get the classical limit. It's just not super straightforward. You need to do this little combination. Okay, so let me stop to ask if this was clear, and also to ask how much time I have, because I still have the correlation functions.
We are pretty flexible with the time, so I think you can. I think you can go ahead. We are pretty flexible.
Okay,
with the time.
Thank you. And was this part clear? So these are basically the punchlines for this part.
Monica, could you say what you're deformed in the example of 24 free scalars TTbar deformed? What is the action of your Virasoro symmetries? I mean, if there's anything to say.
So basically, in the case of TTbar, so in the case of TTbar, the field dependent coordinates look like something like okay, maybe I'm not sure. So here, so this is a very heuristic expression, which is not totally correct. We work in a Hamiltonian formalism. So naively, what you have is some field dependent coordinates which satisfy. So it's sigma plus t plus the integral of mu times the right moving Hamiltonian. That's what it looks like it's going to be. However, you again get all these problems with the zero modes of the field dependent coordinates. So in the case of TTbar, it's worse because it seems that the zero mode. So this integral of h right. So you can say it's a new function, and that function is going to have a zero mode that's not determined by h right, of course, because it's the integral. And then you can try to see, can I find some consistent Poisson brackets for the zero mode that satisfy the Jacobi identities of my theory? And we tried for a very long time, and we couldn't. So I think that doesn't exist a well-defined integral of h right that defines the field dependent coordinate in TTbar. So what we're doing now, basically, we're just saying actually maybe it doesn't make sense to talk about the zero mode. We saw that in JTbar the zero mode was just causing problems. So we just find some modified expression similar to this V improved in JTbar, where the zero mode is completely absent. And it turns out that we can find an expression or correction to that excludes the zero mode, and it's still consistent with conservation. It's some sort of ugly expression in Hamiltonian formalism, but it leads to consistent commutators. The thing that we very badly don't understand is the Lagrangian interpretation of the symmetries generated by this guy, by these charges. I'm not sure that was clear.
Okay, I was wondering whether in the presentation with 26 free bosons, there was a construction you could do that would commute with the, part of the Virasoros as the overall Virasoro in that presentation is imposed as a constraint. So I suppose you want something that commutes with these guys. And I was wondering whether in that presentation there was something simple to say.
But I always, I never think of the 26 free bosons. I always think about the 24 bosons in static gauge. My presentation is always gauge fixed to static gauge. But, and I'm asking,
but physically
I'm
it should be
asking what are the symmetries?
I mean, physically it should be equivalent.
Yeah, I guess it should be equivalent. I just I haven't thought about it at all. I'm sorry. So I'm
okay. Thank you.
Yeah. Maybe it's a simpler way to think about it, but yeah. Okay, so now in the last part, let me talk about correlation functions in J1 with J2 and then JTbar deformed CFTs. So as I said, I'm gonna do this warm up first. So J1 with J2 takes me from a CFT to a different CFT, so I really know what I'm talking about. And as I told you, so I had these Ln tildes and Jn tildes were defined to flow in the same way as the energy eigenstates, but I had found that the true Virasoro generators of my theory differed by this sort of spectral flow, operator-dependent spectral flow transformation, where the operator is just, is U1 charge, basically. Now, since my deformed theory is a CFT, I know that primary operators satisfy the standard word identities with respect to Ln and J with conformal dimensions that are, taken from the deformed spectrum of the theory. So in terms of the undeformed conformal dimensions, they have this formula, and charges and undeformed charges, they look like this. Very good. And another thing that I know is that, if I define some fake auxiliary operator or tilde to basically satisfy this flow equation, then just by, conjugating the word identity in the original CFT by the flow operator, so e to the integral d lambda of chi, I'm gonna get this flowed word identities for all t. Okay, and these tildes, actually these tildes, they were first discussed in a paper by Onkar, I think. So these tildes, so they're not physical CFT operators. However, they have the property just because they're conjugating the original CFT operators by the flow, the unitary implementing the flow. They have the properties that the correlation functions in the flowed vacuum are identical to the original CFT correlations of the undeformed operator. Okay, so now the game that we're basically playing is that we want to use all these word identities and the relation between the generators to basically express the physical O's in terms of these unphysical O tildes. And then once we have that relation, we want to compute the correlation function using this nice property. So just solving for the word identities, we get this relation between O and O tilde. So basically, this is some sort of eta, the flow operator, into basically it's basically the scalar fields whose modes are the J's. And this is basically what it is, but okay, we have some particular ordering. And given this expression, it's clear, it's trivial to compute any correlation function that we want, in the float vacuum of these operators. So for example, for the 2-point function, we take 2 copies of these guys, and well, it's trivial. We just need to use BCH relations a few times to commute the current modes through each other and then through the O's. And the end result we basically get a 2D CFT 2-point function as we should, but where the dimension has been shifted in this spectral flow way. We can do the same exercise for 3-point function. We again get the dimension shift and the fact that the OP coefficients are not changed. We can do it for the 4-point function, and we just get some particular factor in front of the O tilde 4-point function and so on. So the point of showing this exercise is that because we have this exact relation between the 2 O's and everything is obtained by commuting things through and then acting them on the vacuum, we can get any correlator of the O's in terms of the correlator of the O tilde, which are identical to the original CFT correlators. Okay, so that was easy. So now we basically want to take this and use it in JTbar. So in JTbar, the setup is very similar. We again have the physical operators, which are the LNs, which differ from the guys that satisfy the flow equation by this sort of spectral flow relation, except that now the spectral flow is by lambda times the right moving Hamiltonian, which doesn't commute with the right mover. So everything gets a lot more complicated because this is a non-trivial operator. And I should say that also this relation, we inferred it from the classical relation between the generators that might be order h bar squared and so on corrections. I don't know how to fix those. Only these guys have a fully unambiguous definition in the theory. Okay, so we know this. We know that the deformed theory is local and conformal on the left. So we want to define primaries with respect to the LNs, which have these conformal dimensions. These are the ones that I got from the spectrum. So the undeformed one plus this, momentum-dependent spectral flow business. And the last comment is that I have to be working in momentum space, at least on the right moving side, because my theory is non-local, so I don't know how to define things in position space. So I'm going to be in momentum space, and finally I'm going to have to. So I'm going to be working on the cylinder. But at the end of the day, I want to take the radius to infinity limit that has to do with some problem with the difference between the float and the SL2R invariant vacuum. So I want to wash that out, and it only washes out in the Argos infinity. Okay, so defining the primary operator. So as I said, I'm going to be in momentum space. These are the word identities on the cylinder in momentum space. For the left movers, I really know what I'm doing because I basically have CFT relations, so I can just fix the relation between O and O tilde. Again, I'm defining the O tilde with the flow equation as I did previously. So basically playing with the left side of the word identity fixes this particular relation between the O's and O tildes, and I also have the Fourier transform to momentum space. That's good. And the right moving side, I don't really know what to fix because the unflowed right moving generators, these LN bars, I mean, they satisfy just some junk algebra. I don't know what to impose as word identities. So basically what I do, I just make a guess for what the right moving relation between O and O tilde should be. And the guess is very simple. It's analogous to the left moving relation. So now I made this guess for my operator, and now since it's a well-defined expression, I can just compute its commutators with all the symmetry generators and see what I get, check that I get nice word identities. So on the left moving side, they're basically built in to look like this. So I guess I just get the shifts that I put in the conformal dimensions. And on the right moving side, I get something that looks very similar to the above, plus some additional terms which come from the non-trivial lack of commutator of H right, which is the spectral flow operator with the generators, which are some ugly terms. But the point is that these terms go away in the infinite radius limit for the cylinder. So these terms stay finite, but these terms go away. So that's another reason to want to take the R goes to infinity limit. So in the R goes to infinity limit, the algebra of the right moving unflow generators also becomes Virasoro because the corrections were corrections in 1 over R. And I'm basically getting my operators just satisfy the standard CFT momentum space word identities with respect to this. Okay, so I've showed you what the operators are. I've showed you they have nice word identities in momentum space when I take R to infinity. And I can compute some correlation functions. And the correlation functions are computed in an identical manner with the G1 with J2 correlation functions I showed before. So basically what I'm going to get extra is some Fourier transform. And then for the 2-point function, so basically here, this is the same as this calculation. So basically I'm just going to get the expected shift in the conformal dimension, but now it's going to be by the momentum dependent. Okay, so basically I get a 2D CFT momentum space correlator, but with the dimensions replaced by this particular momentum dependent conformal dimensions. And similarly for the 3-point function, I can actually compute arbitrary correlators. And okay, so this is it. The claim is that there is some notion of analogues of primary operators in these theories that are defined in momentum space because this is the only thing that I can make sense of. So far, and they have correlation functions that are completely fixed by those of the original CFT, and they look like the correlators of the original CFT with these shifts in conformal dimensions at the level of 20. Okay, so this is, I'm way over time, so okay, so this is just, recapitulating what I did. The correlation functions are entirely fixed. There are a lot of things to still understand because all of this was in momentum space, but the field dependent coordinate transformation was in position space, and it would be nice to understand better, how that plays out and so on, and a lot of other interesting questions. Lesson for holography. Let me just say to complain about two things in holography. In holography, so the TTbar and JTbar are dual to ADS3 with mixed boundary conditions. We computed the asymptotic symmetry groups a few years ago for those spacetimes. This is how we first knew that there were Virasoros in the game. Those Virasoros turn out to be the inconsistent Virasoros that I complained about, the ones that don't have good commutation relations. So it would be interesting to redo this analysis in holography and see if there's something that we can learn about how to properly do holography in this case. And this is the case of single trace TTbar. It's some setup proposed by Kutasov and collaborators. It's very nice because it makes a link between TTbar and non-ADS holography, which is the thing that's really of interest. There's really this question about symmetries again. We have some field theory argument that actually the symmetry, so this is related to a symmetric product orbifold of TTbar deformed CFTs, and we have a field theory proof that the Virasoro symmetries that I talked about survive the commute to the symmetric product orbifold if you wish. So we expect them on the gravity side again. And it would be very nice to make that work or understand how that works and also generalize this to, more general backgrounds in string theory and try to extract some general lessons for non-ADS holography. Okay, that's all. Thank you.
Thanks a lot, Monica. Are there any questions? Okay, if not, let's thank the speaker again.